So, welcome everyone to the week 3 tutorial session of Galois theory course MA70. Today we will discuss questions related to the assignment, basically the same assignment of week 3 non-star non-blue questions. So, let's begin. Sorry. Show that the Q vector subspaces Qi and Q root 2 are isomorphic, but they are not isomorphic as fields. So, of course, okay. So Qi and Q root 2. So these are of course fields because you can check all the properties. These are fields. You have F by G. You have inverses. Basically, these are rings, and you have inverses also. So these are fields, and these are vector spaces. Q vector spaces. So it has been asked, these are isomorphic as Q vector spaces, but they are not isomorphic as fields. So do you have any doubt if these are fields or Q vector spaces? I can explain it. Okay. So, okay, how shall I proceed? Can anyone let me know? So first we just take these spaces as Q vector spaces. So we have to show that these are isomorphic. So what is the meaning of isomorphism in terms of vector spaces? What kind of isomorphism?
Bijection, and there's a bijection that preserves addition and that preserves addition, is it?
Yes, addition and
I'm not sure. Maybe the zero. I'm not sure. I don't remember the definition.
So yeah. So vector space isomorphism are your basic this linear maps. So these are Q linear maps. So as you have studied, you must have studied in linear algebra. We only talk about linear maps because there we talk about vector spaces only. So yeah. So Q linear map, that means it should be, as you said, it should be additive in the sense that, okay, I use a notation T, but anyway, transformation. So let's say this is phi. So phi of x plus y should be equal to phi x plus phi of y, where x and y belongs to, okay, I can even generalize it. So yeah. So phi from, let's say, vector space V to vector space W over K. K is your field over which the vector spaces are defined. Field K. So then phi is a K linear map if phi of x plus y is equal to phi of x plus phi of y for all xy belongs to V, and phi of ax is equal to phi of ax for all a belongs to K and x belongs to V. So these are the definition to begin with. Is this clear now? So vector space isomorphisms are, so vector spaces morphism or homomorphism, we really talk about the linear maps here. Okay, so let's see. In our case, we need to define, okay, do you know anything else about isomorphism of linear maps? How can we even say that when is it a isomorphism from linear algebra course? I'll definitely explain. Do you remember? Anyone? So when is it an isomorphism? When is a K-linear map is an isomorphism?
If the mapping is unique.
Mapping is unique.
In the sense that not met, like the sets have to be of the same size, roughly speaking.
Yeah. So what does it mean to have the same size? You are correct, but what exactly mean by
so there's
size
a 1-1 mapping. basically.
If we can represent by invertible matrix, so that is that.
Right. So, what exactly we really talk about in vector spaces in terms of like, yeah,
Dimension.
yeah, exactly, dimension. So, vector spaces are defined, so basically, size of vector space is defined by the dimension over K. So, if the dimensions are same, as you said, size are same, invertible matrices you can have. So, all this thing, all this thing are related to if the dimensions are equal. So if you can say that the dimensions are equal, then this is an isomorphism. So in our case, if dimensions are equal, then we can directly say that these are isomorphic. So yeah, you can even check with these properties. So phi K linear map is an isomorphism. So phi is an isomorphism. If the dimensions of the domain and codomain vector spaces are same, dimension of V and W are same. So let's see, do we have here or not? Of course, we need to prove that, so we should have, but let's see why is that. So okay, so now let's see what do we know about Qi and Q root 2. So let's go back to the definition of algebraic elements. So which okay, so I want to consider, so you know that there's this morphism, so K algebra homomorphism, okay, the notation. So you have Qx, so Q algebra homomorphism, I am talking about Q algebra homomorphism. Qi2, you map it to the bigger field. So now here the field is like you have I, you have root 2. You can just take any field which you are comfortable with, where you know these elements belong. So you can, for I you can take complex numbers. This is of course Q algebra, and Qx is a Q algebra. So you define this map epsilon, as you know from the notation, I comma Q. So this map, any fx, it will map it to f of I, right? So from this map we know that Qx modulo this kernel, I should say kernel of this should be isomorphic to C as Q algebra homomorphism. So Q algebra homomorphism means or I just say Q algebra isomorphism. As Q algebras, these should be isomorphic. So that means it should be a ring homomorphism, and it should be a vector space homomorphism also. It should be a vector space homomorphism. So both of this should be there in to say that this is a Q algebra isomorphism. So two things, ring isomorphism, and so ring, or you can, here you have fields, you can even say these are isomorphic as fields, field isomorphism. And second, it should be a Q linear map. So vector space isomorphism means linear map. So these two things should be there. I should write image of this map, not the whole space. Okay, so let's see. Can you tell me what will be the kernel, as you know that this should be a principal ideal. It should be generated by one element. So can you suggest one? Because for I you need to find a polynomial, a non-zero polynomial which vanishes on I with coefficients in Qx. What can I take?
X squared plus 1.
Exactly, very good. So you can take x square plus 1, and this is monic, this has degree 2, and you know that I does not belong to Q, so it cannot be generated by single like x minus 1 thing. So so it should be, so this is the one which we need. So this is really a minimal polynomial because this is monic, has degree 2. So what can it have? It could have degree less than that, but it is not possible because if it has degree 1, then it should belong to Q. I should belong to Q, but that is not the case. So this is really a monic polynomial. Okay.
Yes,
Sorry,
ma'am.
yeah.
Ma'am, I am not getting the point. Minimal polynomial which is generated x square plus 1.
Right.
How we claim that it will be generated by particularly this equation?
Okay, so you know that kernel of so the QX is a PID, principal ideal domain, because Q is a field. So QX should be
Yeah.
yeah, it is generated by, so any
Hmm.
ideal will be generated by single element. First thing.
Hmm.
Now we need to find that element if we can. Okay, so I picked x square plus 1 because I know this belongs to kernel for sure. Now if this is, so firstly this is monic, so that condition is satisfied, but let's ignore for now. Now for minimal polynomial, what should we have? If so let's say mu I and you have Q, that is your minimal polynomial, the usual notation of Q of I in Q. So this is your minimal polynomial. Now what should happen if this is your minimal polynomial? It should divide x square plus 1 because x square plus 1 is in the kernel. So so we know that this kernel should be generated by mu iq. So mu iq should divide x square plus 1 because x square plus 1 belongs to this set.
Yes.
So now what choice you can have? So if you pick something of degree 2 and it divides x square plus 1, then it has to be the same, right? It could be just the multiple, because we are in because division algorithm is there, so we don't have like different representations, and so this is a UFD, so we don't have such kind of a problem. Now if this is, so what choices it could have? Either of degree 1 or degree 2, right? So 2 is cancelled. Now if it is of degree 1, it is a monic polynomial, so it will be like x plus a or x minus a, whichever representation you can take. But that means I minus a should be 0, and a belongs to, so this belongs to qx. So I minus a should be 0, and a is a rational number, but iota, you know, that is a complex number which is
No,
not
contradiction.
contradiction. So x square plus 1 should be the one which is so this is the minimal polynomial.
Yes.
Okay, great.
Okay.
Yeah, so you have this, so that this implies qx over x square plus 1 is isomorphic as again Q algebra with Qi. So one more thing, do you understand? I hope you, okay. This and this, these are same. So firstly, what is the meaning of this? What is the meaning of this? You have all the polynomials fi, fx belongs to Q, and in Qi you have, so this is, so okay, so this is Qi, and Q this small bracket I means you have all of the kind this, where fx, f and g belong to wait, yeah, so this belongs to Q x, and here you will allow fx, f by okay, you will allow fg belongs to qx. Both are polynomials where g of I is not equal to 0. or maybe g of x is not equal to 0. So basically it says you have all the all of this kind, f of I by g of I, all the like rational polynomials, not polynomials,
Ma'am,
sorry. Yeah.
Q open bracket I have read in dummy put a there how can I assume this form would be like this f of I by g of I.
Mm-hmm. I didn't get it.
How can I assure the form must be f open bracket I by g of I, this
uh,
type of.
yeah, this I didn't get it. So this is your you have this set, I'm saying. I'm not saying anything more than that. So this
Is
is,
it definition?
yeah, this is a definition. So like,
Okay.
yeah, as a definition, so square bracket represent just the polynomial evaluations, and small bracket, so I'm just saying square bracket, sorry, small bracket, that represents all the rational ones like f of I by g of I, where g of I is not equal to 0.
So the second one is a field by definition, is it?
Yeah,
And the
this is
first
a,
is
yeah,
only it
exactly.
is only vector space.
Yeah, even
Yeah.
even this is the smallest field. So in place of I, you can take any number or any x. You can take x,
Any
or
indeterminate.
yeah, smallest field containing q and I. So this is this by definition. Okay, you can even prove
Okay,
that
thank you.
these are same. Yeah. So basically what you are doing, you are taking all the, so smallest, so this is really an extension of qi to make it a field. So for example, when you try to do z, so when you consider z, you try to from this, if you want to make a field, you go to q. So this is just the field extension in that sense. So not field extension, that is a bad word to say here. So to complete it in the sense that it has inverses, you put those elements and you get z to I, sorry, uh, is it q, yeah, q is a rational number representation, rational number set of rational numbers. So
No, I mean
yeah,
to say, so you are basically just making the smallest spanning field, right?
yeah, smallest
Okay.
spanning field. So you introduce yeah, I, and you want it to be, so like you want it to be a field, so you allow inverses and you get this. So I'm saying, so this is a good exercise to do, or I can give you an intuition at least. So q, if, so in general I am writing, if x is an algebraic, or maybe x is algebraic over a field k, okay, x belongs to some bigger field L, and L over k is an extension. Yeah, so x belongs to L is algebraic over a field k, then kx is same as kx. This is not true for a transcendental number. So you know that so you know that capital X variable, this is a transcendental number. So, and you know that kx is not same as kx, because you have inverses, and you cannot so basically you cannot prove that this, not cannot, you can prove that these are not equal. Now, why this is true in algebraic case? So you really need inverses. So what you can do, so you, for let's say, so what you want, for example, you need the inverses. So so try to prove that 1 by x belongs to kx. Okay. So this is a good exercise to do. Try to do that. So if you can prove that, then you can really do this generalization.
Yeah, understood. Thank you.
Yeah.
I have to prove 1 by x belongs to k
X.
square bracket x.
Yeah, yeah. So x is an algebraic. So don't think x is a variable. It's a number. So for example, in the case of qi, and you have qi. So just like here, you can rationalize this. So
Basically,
yeah,
a sort of conjugate exists which
yeah.
will ensure that the base will vanish and only it will appear in the numerator.
Yeah, you can say that. And now, so for example, if you prove that, you can do that, right? So what is your question? Sorry.
No, no, I said, so the idea is that there exists a conjugate of sort that
Hmm.
ensures that there is no denominator, it moves to the numerator. Like basically, if it's root 2, then you multiply it, divide by root 2. If it's
Right.
I, again, the same thing, right?
Right, right,
So
right.
basically, you can eliminate the denominator and only ensure that the x
Exactly.
moves to the numerator.
Exactly, but this is the case for I and root 2, because you know that how can you just for example, if you have this and you have something like 1, then you can just multiply a minus b root 2 and a minus b root 2, and you can get rid of root 2 in the denominator. But what can you do when x is some algebraic number? Root 2, you are some kind of using
No,
how.
there exists some polynomial
Yes, yeah,
equation such that
exactly.
it will vanish.
Yeah, it will vanish. And now now try to prove that 1 by x, you can write 1 by x in terms of some in terms of polynomial in kx. So
Yeah, yeah, yeah.
yeah,
But that does not happen in the case of transcendental
yeah,
because it cannot be expressed as a polynomial.
exactly. Because if this is the case, then it has to be a algebraic number. That is not true.
Understood.
Yeah. Okay, so if we sometime write a square bracket or this small bracket, then these are same. So you don't need to be confused by that. So this is a field, and we talk about, so we can use any notation if we want. Okay, so okay, so where were we? So I can even write it to be this. Okay. So this is a Q algebra isomorphism. So from this, and from this property that, okay, I'll write again, x square plus 1 isomorphic to Q I. I don't need to write this much, but next, that degree of mu iq should be equal to the dimension or degree extension dimension of qi over q, that we also did in the notes in the lectures. So degree of the minimal polynomial is really, why is this true? Because these are isomorphic as vector spaces. So I'll write q linear. So these are isomorphic as vector spaces, so the dimensions should be equal. Now dimensions are equal, and what is the dimension of qx by x square plus 1? You know that in this ring, so actually this is a field. So in this field, what you can get, that will be just like a plus b, and yeah, so okay, a plus bx, where just a plus bx, yeah, a and b belongs to q, because you are going mod x square plus 1. So whenever a square occurs, you can get rid of that square, and you can just pull it in the remainder. So remainder is really of this form. When you divide fx by x square plus 1. Okay, so dimension of this, because of this, dimension should be what? So this implies dimension of qx, yeah, dimension should be 2, exactly. So dimension is 2, and because of this, dimension of this is really, so we can say this is really the dimension of this left hand side should be the degree of the polynomial, minimal polynomial, and that has to be equal to dimension of qi. Okay, so you have dimension of qi, Now we also need to figure out what is the dimension of q root 2. So, sorry, that we need to figure out, but yeah, we need to prove that this is 2. So again, can we do something of this kind, like as we did for I? We can again try to use the isomorphism, use this map root 2 comma q, which maps it to q. Okay, I'll again take C or R, anything is fine because we are really concerned about the image. So you can take or R because both are fields, so we have no issue. And root 2, we are talking about root 2 and we know that root 2 belongs to R, so we don't need to extend it to C. So from this map we know that f of x should map to f of root 2, and again you can prove that mu of this. So can anyone tell me what should be that? What should be the minimal polynomial for root 2?
X square minus 2.
Exactly, x square minus 2. Very good. So because you know for root 2 you can pick x square minus 2. So this, so to begin with, x square minus 2 belongs to kernel of this, and again you can prove that this is minimal, and so this is minimal. So we have the isomorphism x square minus 2, that is isomorphic to, again we are concerned about q linear map here, but this is a q algebra isomorphism, so we have extra ring homomorphism also. And now we have to take this. Again, root 2 is algebraic because you have this polynomial x square minus 2. So root 2 is algebraic, so q root 2 square bracket or a small bracket, both will work fine. Both are the fields, both are same. So again, this implies dimension of q root 2. So dimensions are same of LHS and RHS. So this should be equal to degree of mu root 2 q, and that is, what is this? This is equal to x square minus 2. So degree should be 2. So that's why dimension is same, and you have so what map you can define? So if you have the same dimension, you have basis of same cardinality. So what you can do, you can just map one to, like, you can just give a bijection of this set and you are done. Is that clear?
Ma'am,
Yeah.
please repeat this one.
Right. Sorry, which one?
Sorry, there's nothing to repeat.
Okay. So the Siri. Yeah. Tell me which part I should repeat.
Last line.
This one. Okay. So you understood that. So is this clear? This part.
Yes.
Okay. So we are saying, so these are isomorphic as Q algebra. So Q algebra isomorphism means this implies this is ring isomorphism. These are plus vector space isomorphism. That means vector space isomorphism. That means Q linear isomorphism. So Q vector space isomorphism. So there is always a field. So Q linear. So you know that these two fields are these two vector spaces are isomorphic as so these are isomorphic as Q linear because of Q linear isomorphism. So this implies whenever this is the case, whenever these are isomorphic, dimensions are same. That is the result we are using. So dimension of Qx as Q vector space same as dimension of Q root 2, again as Q vector space. So now what is the dimension?
2.
Yeah, exactly. Degree of x square plus 2, x square minus 2, because this is minimal. Okay, and
Yes.
yeah, so this should be equal to dimension of Q root 2 SQ vector space. So this is equal to 2 and we get this. Is this clear now?
Yes. Yes. No.
Okay,
Thank
great.
you.
Yeah, sure. So yeah, dimensions are same. So as I said, whenever dimensions are same, you have a basis. You have basis for both Qi and Q root 2, which has same cardinality. So you consider any basis for Qi and Q root 2, and it has same cardinality. So as a set, you just map, you just give a bijection of these bases, and when you have the bijection, then you can just extend it to a q-linear map. So this is really how we can construct even isomorphism if you have same dimension. Okay, so these are isomorphic and we are done. Okay, so qi and q root 2 are isomorphic as vector spaces, SQ vector spaces. So you have a field also. Okay, so now we need to prove that, or we need to prove that Qi and Q root 2 are not isomorphic to show isomorphic as fields. So let's see. Okay, so firstly, these are fields that we have even know now, because you have because this is really a smallest field containing Qi for the first one, and smallest subfield of C. So we should say that smallest subfield of C, which contains Q and root 2. Okay. So what we all need for a field isomorphism? So for a field homomorphism, what should we prove, or what should we know? So phi is a field homomorphism if so this is a ring homomorphism. It's just ring homomorphism and field homomorphisms are same. Like at the place of rings, you are having fields. So that should be again phi of and I'm just writing in a
Preserve
general.
addition and multiplication.
Exactly. So you have multiplication, preserves multiplication and addition. And one more thing, we always assume for our case, identity of the first one should map to identity of this. So here you know the identity is just one in Qi or Q root 2. So identity should map to the identity. Multiplicative identity should map to multiplicative identity. So these three things means this is a field homomorphism. And now for isomorphism, we should be having bijection. So this, sorry, field homomorphism. And now if we add bijection, we'll get field isomorphism. So let's see if we can construct or not. Okay, so let's assume there is one, and let's see if that can be a field isomorphism or not. So okay, not field isomorphism, or just we will try to get a contradiction. So I am just doing here, let a field isomorphism phi. Okay, so you have this much information. That means, so for a field homomorphism, you must be having what? So to define a field homomorphism from this to this, can you tell me which element I should be concerned about? Or so you know that 1 goes to 1, and you know that phi of x plus, so x plus y goes to phi of x plus phi of y. So you can really, you know that any n will go to n for all n belongs to z, and even you can even do for rational extension also. So you if you have p by q, that will map to p by q, because you have this multiplication also, x into y. So belongs to z and q is non-zero. So you know that q goes to q, fixes q. So every element of q goes to this same element under phi, if this is a field homomorphism. Now what we really need to define, not define, what we really need to think about, which element, like q is fixed already,
I.
so let's say where I goes, because these are, we don't have any choice for q. So we can have choice for I, or wherever it will go, it will be some element of q root 2. So a typical element of q root 2 will look like this, where a belongs to, I have already assumed phi is a mapping, which is a field isomorphism. So I am saying I is going somewhere in this map. So for some AB belongs to Q. Okay, so so from these three properties, and knowing this, so what can I do to get a contradiction? Of course, we need to get a contradiction. Yeah.
Phi of I square must be equal to I into I, which is going to be a plus b root 2 whole square.
Right. Exactly.
And phi of I square is minus 1, which is minus of phi of 1, which is 1.
Right.
Minus 1, so totally.
Yeah.
And we can now further prove that there does not exist any rational number that satisfies. So from here, I think you'll get either a should be 0 or b should be 0.
Right.
Based on which you will get that a square should be minus 1 or b square should be minus 1 by 2, and none of that will be satisfied.
Exactly. So, yeah, exactly. You proved it. So even we don't need to even go further. So this is minus 1, and so as he said, you just take so you use this property of multiplication, which says phi of x into y is equal to phi x into phi y. So you just consider phi of I into I. So these are two elements of qi, and that from the property it should be equal to phi of I into phi of I. And so I'll go from, so here phi of I is equal to a plus b root 2. Again same thing, a plus b root 2. So you get something a plus b root 2 square. From other side, what will you get? So phi of I square is equal to, that will be phi of minus 1, because I square is minus 1, you know that from iota. So phi of minus 1, as we already said, n goes to n, for all n belongs to z. So this is minus 1, and in this part you can even do this thing, a plus b, a plus 2b, sorry, a square plus 2b square plus 2 root 2b, oh, ab. So a square plus 2b square plus 2 root 2 ab. Now from as these two things are same, it should be equal to, both of these things should be equal. So again, if you compare it, because these are rational numbers, so so a, and since a and b are rational numbers, we should be having a square plus 2b square is equal to minus 1, and 2ab should be equal to 0. So as he said, even this cannot be a possibility, because square sum of two positive numbers, because a square is a positive number, b square is a positive number in rational numbers. So these two, a square plus 2b square, has to be a positive number, and so that cannot be equal to minus 1. Even you can further You can even further do that. From this property, this should imply A is equal to 0 or B equals to 0. And if you apply here, if you say one of them is 0, in any case this cannot be equal. So basically this cannot happen, which is a contradiction. Okay, is that clear?
Yes.
Okay, great. So here what we did, we considered there is a field homomorphism, and we proved that so I has to map to somewhere. We defined I maps to A plus B root 2 because that is a typical element. So it is mapping to Q root 2. It is so there should be an element, let's say A plus B root 2, and we proved that such A and B cannot exist, and and hence phi cannot exist. So we get a contradiction. So there is no field isomorphism here. So we are done with this part. Okay. Let's see the second part. Okay, just copy these two maybe. Okay. Anyway, so okay, we are doing B part now. Let Z belongs to C be a square root of Z is a square root of 2I. So we have been asked what is the degree of field extension QZ over Q. So this is same as, so whenever degree has been asked, so degree is really the dimension of vector space QZ over Q. So the degree is, by definition, is this. So dimension of QZ over Q as a vector space. Is that clear? Okay.
Yes, yes.
Yeah.
Yes.
Yeah, great. So let's see. So Z belongs to C be a square root of 2I. So what should we do here? Can anyone tell me how shall I proceed? Okay, let's think what is the square root of 2I, because we okay, so let's see what we need. So when, as we did something earlier, we are talking about the dimension of QZ, and you have seen that dimension is same as minimal polynomial of Z over Q, because we are talking about dimension over Q. So if we can find the minimal polynomial, and it's, of course, if we know the minimal polynomial, we know the degree. So that degree will be equal to the dimension. So that's the plan. If we can find the minimal polynomial of Z over Q, so we will get the degree and we will get the dimension. So from the mapping, this epsilon ZQ, QZ, or okay, again I can take, so we are talking about 2I, we can always take the algebraically closed field C, which is a Q algebra, and you have QX. Okay, so again from the kernel we will get this thing. So let's see what is the minimal polynomial of mu of Z over Q. So any thoughts? So square root of 2I. So this might be plus minus. So if I'm already writing root, I'm thinking of positive, so I wrote plus minus. So you can actually do some clever thing. One option is always there. You can see Z square is equal to 2I. From this you know that Z square, so you need to find a polynomial, right? So so let's see what is a polynomial we can consider, so that Z is a root of that polynomial. You can take so from this information, let's try to do that. Z square is equal to 2I. This implies even I can go further, I can further square it and I'll get 4 minus 4, right? Because I square is minus 1. So I have one polynomial. So at least I know this is algebraic. Even, yeah, so at least I know this is algebraic. So z raised to power 4 is equal to minus 4. That is one polynomial which could be a candidate, which is a candidate for a minimal polynomial if we can prove that there is no polynomial of degree 2, degree 3, degree 4, sorry, degree 2, degree 3, or even degree 1. Of course, degree 1 is not a possibility because this does not belong to Q. So, because if there is a polynomial of degree 1, that this should be the polynomial, right? So that means this has to belong to qx, but z does not belong to q, so this is not a possibility. So one degree is not a possibility, but let's see 2 or 3 could be there or not. So again, what do you think?
Isn't possible.
Sorry,
I mean, degree 1, degree 3 are not possible.
degree 3 is not possible. How?
I can't think of a formal solution.
Sorry, come again.
I don't have a formal explanation in mind.
Okay, sure, no problem.
I think complex roots occurs in conjugate pairs, so degree 3 is not possible.
Okay, right, yeah, that is, of course, yeah. So we are in Q, so in reals we know that yeah, conjugate, it will appear in conjugates. Yeah, exactly, it cannot be 3. But one
I have
thing,
a general doubt here.
sorry,
I've been
but
given
yeah,
that it is a
sorry,
square root.
that has that even okay, sorry, one thing I just want to comment, it could have a real root. So it could be like, yeah, but if you can separate this real part and complex part, then it will be great. Complex roots will always occur in conjugate, but there's a possibility that you cannot separate. These are irreducible, so you can have something, for example, this, for example, this, yeah, any prime, and you have any degree. So this is a irreducible polynomial so this is a irreducible polynomial in qx, but you cannot separate real part here, because you know that cube root of 3 is a real root, but you cannot separate it because this does not belong to q. So yeah, 3 could be a possibility, first thing. Yeah, okay, so yeah, there's a clever thing here. You can actually do something with 2i. You can write 2i to be plus 1 minus 1. So if you can write it to be this, and because of this, so it's like a square plus b square plus 2ab. So this is like 1 plus I square. So yeah, this is somehow become a square of some complex number. So because of this, you have, so z is really a root of this number. So this is plus minus 1 plus I. Now you can actually see that, so you have some complex number which is not even a root of something. So you can, so what I can do, I need to construct a polynomial. So I'm saying that we can even have a 2-degree polynomial because of this condition. So z, when you, so I'll just consider one anything, like let's say, let's try to find some element in this kernel of, so kernel of 1 plus I comma q. Let's try to find something here. So in this, so I really want to talk about just plus 1, plus part. So you just square it, so you will get, what will you get? You will get 2i, as we really did. So 1 plus I square is 2i, right? So 1 plus I square, that is 2I. Okay, now you need to write it in the form of z. So what I can write, 2 into z I know is really 1 plus I. I'm just considering plus part right now. So 1 plus I. So at the place of I can write z minus 1. Now I am in a Q. Like 1 belongs to Q. So you will get z square minus 2z plus 2 is equal to 0. So this is a polynomial which z satisfies. So f, you can consider fx to be x square minus 2x plus 2. Is that clear? So this is a polynomial which belongs to kernel of 1 plus I into q. Oh, I should not write like this. This is kernel of 1 plus I comma q. Is that okay? Any doubt? I hope so. Any doubt? Anyone can confirm so that I'll know that there is no network issue.
No doubt.
No,
Okay,
no
thank
doubt.
you. Yeah. Okay, so you get a 2-degree polynomial. Now you can again okay. So this again I will claim that this is a minimal polynomial of 1 plus I comma q. First thing, it cannot, so if so mu has to divide fx and fx is of degree 2. So again it cannot be, this cannot be of 1 degree. So the possibility is degree could be 1 or 2. So 1 is gone because it does not belong to the root of 2i, which is 1 plus I. That is that does not belong to q. So degree 1 cannot be a possibility. Now degree 2. So just to be sure, you cannot have any other polynomial of degree 2. So if there is, so for example you have some x square plus ax plus b, there is any other polynomial which is mu. So my claim is that has to be equal to this. Otherwise, if this is not equal to x square minus 2x plus 2, then what you can do from division algorithm, so x square minus 2x plus 2, so this has to divide. Okay, so this into qx, okay, so qx plus rx. So if these are not equal, then rx has to be something of the kind x of degree less than degree less than or equal to, sorry, less than or equal to 1. So that means when you put z here, okay, don't confuse by this q. I just wrote some representation. So it's a small rx and a small gx, some polynomial. So when I put z here, that will become 0. This will become 0 because mu is a minimal polynomial for 1 plus I. This is 0, so this has to be 0. So r of z has to be the 0 polynomial. So now so this is of degree less than or equal to 1, and we already know this cannot be the case. So these really have to be the equal quantities. Just could be a multiple, but we are already with monic, so both of these are monic, so gx has to be 1. Is that okay? So this is x square minus 2x plus 2 is the minimal polynomial, mu of 1 plus I q. Similarly, you can do with the case of minus 1 plus I. So when you take this, z is equal to this, then what you can do, z square will be 2i, and you can write 2 at the place of I. Now what I will write, I is equal to, so minus z minus 1, so minus z minus 1 So I'll get z square plus 2z plus 2. So that will be my minimal polynomial. So this implies mu of minus 1 plus I comma q x is equal to x square plus 2x plus 2. Is that okay? Okay, I hope so now. So now you have the minimal polynomial, and so you have the degree that is equal to 2. So dimension is really equal to 2, which they have asked. So this is equal to 2.
Yes, ma'am.
Yeah.
As if, we have defined QH to C map defined epsilon Z comma Q.
Yeah.
It, meaning of the notation epsilon Z comma Q.
Sorry, I didn't get your question. So mu of z comma q. Yeah, this we need to find. Yeah. Sorry, come again.
Notation meaning of the subscript notation.
Okay, subgroup notation.
Subscript.
On that arrow on the previous page, I think you have q of x maps to C on the right side.
Oh, okay. Q. Yeah, right.
Yeah, this one. I think that is that the question?
Yes.
Yeah, this is the map from which we are getting this mu. So this map says you have this epsilon z comma q, and you fx will map to f of z. This is the map. And
So this is a homomorphism, is it?
Yeah. This is a Q algebra homomorphism. So Q algebra homomorphism means this is a ring homomorphism, and this is a Q linear map. So as a vector space homomorphism and as a ring homomorphism, both of this combinedly imply that this is a Q algebra homomorphism, because these are Q algebras. Sorry, QZ and C are Q algebras. So algebra.
Did I need to do abstract algebra properly to continue with the course, or is this level enough?
Okay. So
I am a CSE student, so I have only done discrete maths, and that had some coverage, but very little.
I'm not sure how much, but yeah, so I'm not sure how much you need, but I'll try to explain as much as I can. If you have any doubt, you can even mail me, or if you even I will try to explain as much as I can.
No, I'm able to understand till here. Just the words and those things are new to me.
Okay. So this map is a part of the course. So you just need some definitions which you can easily read it up, or even you can ask. So I think that will be sufficient.
Okay.
Yeah. Just field theory, ring theory, group theory. These things have been assumed. Just the basic ones. Okay. Okay. So now is it clear? So we have this map, and from this I explained here, so that's why I have not explained it again. So at first, right. So you have this map, and you get this isomorphism. So from this data you get this isomorphism, and we use again and again. So this kernel is generated by the minimal polynomial of whatever element you are considering as algebraic element I comma q. So this kernel is this. So here again what we did, we had this. So change the color. Okay, so you have this. From this you get qx mod so mu z q isomorphic to q of z. Yeah. So as you can see, we for the minimal polynomial for the map, we even don't really need to write again and again what is the map, because from this notation itself we know that this is the map. It maps fx to fz, whatever element written here, and we are considering polynomials from qx. So whatever field is there, polynomial ring of that field. Okay, so this is the notation. Even for minimal polynomial, it contains all the information which we need. We don't really need the information of C. We just need a algebraically closed field which we can take as a codomain, because to define a map we should always have a codomain. That's and even a Q algebra here. So yeah, just that. So we don't really care about what field we are taking, but it should be compatible with the information, because at the end we need the image only. So yeah, image is, so this is image of qz, qx. Yeah, okay, is that okay now?
Okay.
Okay, great. So okay, let's see the C part. Z comma w belongs to CB algebraic numbers with the minimal polynomials to be equal to x square minus 2 and x square minus 4x plus 2. Show that there exists an isomorphism between these fields. So as we have seen it, okay, first thing you have seen, when you have x square plus 1 or x square, okay, make some space. So in the first part you have seen that x square plus 1, you have this x square plus 1, and you take x square minus 2. Even the same degree ones need not be isomorphic as fields. Degree only proves that you have a vector space dimension to be equal. So these will be isomorphic as vector spaces. So what I mean to say, if the minimal polynomial are of same degree, then these are isomorphic as vector spaces. But if these but we cannot say anything about the fields. We cannot say anything about the field isomorphism. So in this case, these are not isomorphic. In this case, we need to prove that these are isomorphic as fields. Okay, so just try to understand what is the difference we really have in these two parts. Okay. So of course, degree is not enough. Okay, so let's see this question. So you have qz and you have qw, and minimal polynomial of zq is given to be x square minus 2, and wq is given to be, so this is really a polynomial, x square minus 4x plus 2. I think that's that. Yeah. So we need to find the isomorphism between these two fields. So yeah. So okay. So okay, what is qz and qw? If we can figure that out from this minimal polynomial definition, that will be a good candidate to prove or whatever, to give isomorphism. So let's see, because earlier also what we did, we mapped z to w, and even so we did I map to a plus b root 2 and something like that. So again we just need one isomorphism. So if we can find out what is z and w, then there might be a chance we can get the isomorphism. So let's see, what do we have? Okay, actually here we can directly prove that get the value of z and w. So from this, what you know, x square minus 2, so z is a root of this, so z should satisfy. Z square minus 2 should be 0. So you have Z square is equal to 2 and Z is really plus minus root 2. And what about this? You have W square minus 4W plus 2, that is equal to 0, because a minimal polynomial is from the kernel, so that is the generator of the kernel. So this W should satisfy this equation. That means now as you know, we cannot solve it easily, so we just use the Acharya formula, Sridharacharya formula, that is plus 4 minus b plus minus root b square minus 4ac, that is 4 into 2 upon 2a. So you have 4 plus minus root, so this is 8, that is 2 root 2, and you get 2 plus minus root 2. So QW is Q2 plus, so anything is fine. So it says, so first thing, W is a root of this this polynomial, so any of this you can consider for W. So I can take plus, I can take minus, anything is fine. So but what is my point here? So either you take plus or minus. Can you tell that this is equal to Q root 2? Is that okay? As a set, even like this is a field containing even smallest field, okay, smallest subfield of C, because smallest where, so we should have a bigger set to talk about. So smallest subfield of okay, containing Q and 2 plus root 2 or anything even minus. So I'll just take minus. Don't be confused that we have both of these here. We just have one. Field containing Q and 2 plus root 2, and this is field containing Q and root 2. So is that okay if I say these are equal? Because if we want to prove that these are equal, we should be able to show that any element from Q 2 plus root 2 should be here in Q root 2 and other way around also. So that is okay, right? So
Yes.
yeah. So we don't really need to prove anything further, because we know that QW is Q root 2 and that is equal to QZ. Okay, so what we can do, so even if you have minus root 2, that is also isomorphic to Q root 2, not even isomorphic, as I said, these are equal. Q2 plus root 2 is same as Q root 2, so I'll just write this. So these are equal. This implies QZ is same as QW. So the map, if we can just take the identity map now. So okay, one more thing, as I said, these are equal, and even as fields these are equal. So if I define identity mapping, so okay, so I should force upon that QZ is equal to QW, and identity mapping is always a field. Identity mapping is always a field isomorphism. So we just take identity isomorphism and we are done. And because this is same as Q root 2 and this is also same as Q root 2. Is that okay?
Yes.
Okay. So yeah, we are done for this question then. So in this case, so in general, like for example, you can try to prove that Q root 2 is not same as Q cube root of 2. Like this, even field isomorphism you can try to prove. So okay. Yeah.
Please repeat the question.
So
You
I said q root 2 is not isomorphic to q cube root of 2. I'm not talking about vector space isomorphism. I'm saying okay, cube root of 2 not isomorphic as field isomorphism, as field homomorphism. So this is not not isomorphism as fields. That is also enough to say. Yeah. Even I am not sure, but you can also prove that these are not isomorphic also, like just root 2 and root 3. These are not isomorphic as fields.
okay?
Yeah. So yeah. Okay. Is that okay now?
Why are they not isomorphic?
Yeah. These are not isomorphic as fields. Yeah, I think so.
Couldn't
Just
you do
try
an
to.
identity sort of a mapping where like
Yeah, you try to do the identity mapping, but you will get a contradiction if I have to write it down. I'm not sure, but I think these are not isomorphic. If you take this map, so something should so what will happen, let's see. If you multiply, so root 2 into root 2, if you take 5 of that, that should be root 3 into root 3, that is 3, and this is equal to 5 of 2, and that is 2. So these are not same. So I took so as you said, you take this root 2 goes to root 3, right? You said this.
yeah.
Now this will be the problem. So you take this.
Uh-huh.
Yeah. So this should be equal to 5 of root 2 into root 2 is 2, and that is 2. So 2 is not equal to 3. So you will always get a contradiction like that. See, so even you can prove that any root similar to this, any two different prime roots are not isomorphic as fields, like q root p and q root q, even different degrees. So as a field isomorphism is very strong. Okay.
Understood.
Yeah, great. Okay, let's move to this question. L over K be a field extension. So L over K be a field extension. So we write this picture always. So this is field extension. L is sitting above Q. So for example, R and Q. Okay, so even you can have C. Okay. You have this field extension, and Y belongs to L, and chi is a subset of L, which is an arbitrary set. So you have no condition on chi, just a arbitrary subset. Show that Y is algebraic over K chi if and only if Y is algebraic over K x1 to xn for some n belongs to n, and x1 x up to n xn belongs to chi. Okay, so firstly, you know that algebraic means what? From the definition, so Y is algebraic. So I'll write as a definition. Y is algebraic over K if the map, so if kernel of chi y comma k is non-zero. So what do we mean by that? If you consider this map kx, and now you have this bigger field, you just take L. So kx to L, and this is capital X. So I will write x like this for a small, that is a number or any particular element, and capital X I will denote as a variable. Okay, so kx epsilon y k, and the map says any fx will map to f of y. Okay, in this map the kernel is, if kernel is non-zero, what does that mean? Kernel is non-zero means if okay, so kernel of this map is non-zero, this implies there exists a polynomial, a non-zero polynomial So because I'm saying non-zero, so 0 is always there because y will satisfy the polynomial 0. So everything is a root of 0 polynomial. So there exists a non-zero polynomial, say polynomial, say g of x belongs to q, not q, here you have just general field, such that g of y is equal to 0. So you have, so these are equivalent things. So we always talk about like in the sense of kernel. So kernel is non-zero, that is by the definition if y is algebraic over k. So what we really need to prove, y is algebraic over k chi. So always remember what is the change here, what field you are taking, what k you are taking, that we are concerned about. So let me write some different notation. Let's say for this definition I'll just write f to so that there is no confusion. So you have f, so this is just a field, okay. Yeah, so what we are saying, y is algebraic over k chi means what field you are taking. If you take f to be k chi, then you are in this situation. So k is algebraic, y is algebraic over k chi, that means there exists some polynomial g, non-zero polynomial in f chi, in k chi, if we are saying. So whatever polynomial you are talking about, that belongs to k chi x. And now other side you have y is algebraic over k x1 to xn for some n belongs to n, and x1 to xn belongs to chi. So you are now saying that there exists a polynomial. So you have two things. So y is algebraic over k over chi if and only if, that we are asked to show y is algebraic over k x1 to xn, some numbers x1 to xn, for some n, we are not saying for all, for some fixed n star, or I think, okay, n star means just at least, n star is n equals to n union 0. So you are also taking 0. I hope that is the definition, but yeah, it makes sense here. So 0 is allowed. 0 means okay, 0 means there is a possibility that there does not exist any of this. For example, chi is a empty set, then you can just take no number here, like, so in that sense. And x1 to xn belongs to chi. Okay, so what does this mean, this equation? This means in terms of this polynomial and kernel, what you can say, kernel of epsilon y comma k chi is non-zero if and only if kernel of epsilon y comma k x1 to xn, for again fixed x1 to xn in chi and n belongs to n star, this is non-zero. These two you have to prove this. Now further I can imply that this means there exists a polynomial, let's say g belongs to k chi x. Okay, I hope the notations are clear, such that g of y is equal to 0 if and only if, and also this is non-zero, so that is important, 0 is always there. So there exists some non-zero polynomial, and again there is some, so I'll just write some other h, non-zero polynomial h, there exists non-zero polynomial h belongs to, now you have the field x1 to xn x, such that h of y is equal to 0. So we have transformed this equation to our understanding now. So okay, can you tell me, so here where x1 to xn belongs to chi and fixed numbers, so we are just saying that there are some fixed numbers which is there, and you have this condition. So can you tell me which side is trivial? So there are two sides we need to prove. uh, left hand side implies right hand side, and right hand side implies left hand side. Which side do you think is trivial? Just think about now. There exists some
Right, left to right.
Left to right. Okay. Is it so? So what does this mean? You have this equation. There exists some g belongs to k chi x such that g of y is equal to 0. And here we so basically trivial means, so can you explain how this is true? Left hand side implies right hand side. Trivial means you should be able to just say from this information itself. Of course you can prove that is also, you can say trivial. Yeah.
Because x1 x to xn is a subset of phi.
Right. Yeah. So left hand side implies right hand side, you are saying. I think that's the other side you can trivially say. So trivially say means, of course trivial means there's nothing to prove. So yeah. So you consider this polynomial h.
Right to left is rather trivial, right? Because
Yeah.
x1 to xn is a element of chi itself.
Right,
So-
exactly. Yeah. So so if you yeah, if you assume this, so I'll just change the color. So if you assume this side, left hand side, that means, so there exists some h of this kind. Then if there is this h belongs to this, that means since x1 to xn belongs to chi, this also so this is a subset of k chi x, right? Because x1 to xn belongs to chi, we can say that this polynomial itself, h belongs to this set, and we know that this is non-zero and h of y is equal to 0. So this implies we have a polynomial in k chi x which is non-zero and it is 0 at y. So this condition implies this trivially. You cannot say from left to right because g belongs to k chi x. You cannot say this belongs to k x1 to xn chi, because k chi is a bigger set than this, bigger or maybe equal, but yeah. Is that okay? So you cannot say
Yes.
that. Yeah. You cannot say trivially. Okay, so yeah.
Ma'am, K chi is defined as a field containing K. K chi.
Sorry, come again.
Ma'am, K chi. What is K chi?
K chi is okay. Right. So I should have said that. So k chi, k. Okay. So again, smallest field containing k. Oh, okay. Already we have L, so I should write, as I said, there should be a bigger field to say. Smallest subfield of A, L, containing k and chi. Chi is a set. Chi is just a set. We maybe something like maybe for example you have x1 to xn, you have more elements, and that could be uncountable. We don't have any information about that. Even I'm not sure if I can number it. but there is just some set of L. We have this.
So
Some arbitrary set.
basically we need to prove that the intermediate field between L and K, if it is algebraic over L, so it is algebraic between all the fields if we define K
Right. Okay. Right. Yeah. Yeah. So Y is algebraic. Okay. You mean to say if so Y is algebraic. Sorry. Y is algebraic over A. So what is your proposition? Y is algebraic over K that we have. Okay. Yeah. Yeah. So Y is algebraic over Kx. Yeah. You need to prove that. If it is algebraic over k chi, then it is also algebraic over. I don't know. Come again. What was your last statement?
means that it is algebraic between every field which is between L and K. Intermediate.
So if so, you have two fields. If y is algebraic over k, then no, not really. You can say that it is algebraic over any field in between that. Because for example, you just take R, if I understand your question correctly. So if you take this these three fields, then iota is algebraic over C. Oh, sorry. Yeah, okay. That should be finite extension. That is also required. So, for example, you take this. That should be a good option to take. You take this Q root 2, and you have R. Am I still correct? Okay. Yeah, you can take pi for example. Pi is not algebraic. Okay, but you said yeah, pi is algebraic over R. Okay, because it belongs to R, so you can take x minus pi, but it is not algebraic over q root 2.
Ma'am,
Yeah.
pi is not algebraic over R also, right?
No, pi belongs to R. That is a irrational number.
So when you say algebraic,
yeah, algebraic over
with respect to R, you mean that
there exists
if there's a polynomial equation with the coefficients of R,
yeah,
and x satisfies that. Okay.
yeah, exactly. That's the meaning. You take algebraic over F. You take this field here, and you take G to be in this Fx. Yeah. So if you take this as algebraic over some field, then coefficients of the polynomial should belong to that field. So for example, we have taken R in this case. We have taken pi, which is a rational number, and we know that that is not algebraic. That is not a trivial statement to prove, but we know at least. So pi is not algebraic over q. We don't have any polynomial with rational coefficients such that pi is a root of that, but pi is algebraic over r because it belongs to. So we don't have much of a problem here. For example, you can even take this root of pi. So that is something you can take this q, and even okay, if I have to take 3, so I can take this q root 2. I can take q root 2 comma root pi. Even I can take this. So you know that pi is algebraic because now you can define this root pi. So okay. Am I still? Yeah. I think I'm not answering your question again. But I took a polynomial over Rx. You said okay. Let me write it properly. So you have a chain, or maybe you are saying if there is a number y which belongs to L and y is algebraic over k. Okay. Y is algebraic over any field between that. Sorry, I misunderstood what you were saying. Yeah, so y is algebraic over k. That means there is a polynomial fx such that f of y is equal to 0, where fx belongs to kx, a non-zero polynomial. And as the coefficients are in k, we can always say y is algebraic. So yeah, if y belongs to e, then but anyway, so y is algebraic, yeah, algebraic over e also, right? If you extend your field, so if you take the bigger field, then it will always be algebraic. Yeah, that's exactly the statement we are using here. So if it is algebraic over a smaller field, then it is algebraic over a bigger field also, because the polynomial we are getting, it is of the coefficients are from that field. And if we extend that field, still we can take the same polynomial, because this extended field also contained that smaller one. Yeah, exactly. Sorry, I misunderstood what you were saying. Is that okay for everyone? So we just said that the triviality is here. So yeah, so k chi is the smallest subfield of L containing k and chi. So that means you have you just extend it so that you have inverses and everything. So you just construct some field. So for example, if I just say if this is a countable set, n plus 1, n plus 2, you can take, or you can go on. So you allow inverses in this field. So that's the smallest subfield. You denote it to be k chi. Okay, say so here, so the other side we really need to prove. So other side means to show if, so the there exists, so okay, so let's assume, let there exist a polynomial, non-zero polynomial from this side, from G. Okay, from there exists non-zero polynomial G in k chi x such that G of y is equal to 0. Let's assume this information. Okay, now we need to prove that can we construct some polynomial using the information of G or anything? So can we construct can we get a polynomial, not even a polynomial, can we get a field? So we need to find a field k, some elements, we don't know these numbers, because we need to figure out this, even n we don't know anything. So we need to find some numbers, some elements of chi such that we can get some h. So okay, so I am saying same G we take the same G, but we do something with we try to find this. So claim there exist x1 to xn belongs to chi, there exist n belongs to n star, and x1 to xn belongs to chi, such that G of such that G belongs to k x1 to xn x, just that. So we already know G of y is equal to 0. So I'm saying I can find some numbers x1 to xn such that G belongs to G belongs to k x1 to xn x. So can anyone tell me what candidates I can choose for x1 to xn so that G belongs to this ring? Oh, yeah. Actually, I should write this. That is all. So this is a polynomial ring with this field. Okay. Oh. Oh, that might be a confusion for everyone. Okay, I'm just talking about, I'm not taking denominators, I'm not allowing denominators. If I'm writing variable, that I should be careful because these are transcendental elements. So this is just a polynomial. Sorry for the confusion. So G is a polynomial and H is a polynomial with coefficients in k chi and here coefficients in kx1 to xn. Okay, so yeah, can anyone tell me what can I pick as x1 to xn so that G belongs to kx1 to xn x? Is a polynomial with G is a polynomial with coefficients in this. Actually, I said everything. So what you want? You want the coefficients of G to belong to this field, right? So what can I take x1 to xn to be? Or some n, m, I don't care because we just need one natural number. Anyone? Yeah. Yes.
What look like the term?
Sorry.
How they look like the term k x1 dot xn.
Okay, so this is the field with elements. So as I said, smallest field containing
Huh.
k and chi. So a typical element will be of the form. So okay, so a typical element could be of the form, let's say f. Okay, so f x1 to. Okay. So any polynomial, and think about you can okay, so, elements. Okay, so even squares, cubes, everything is allowed. So it will be like you can have something x1 square plus x1 plus something something x2 square or anything of this kind, plus let's say coefficient could be from k, so let's say a. Okay, so let me write a smaller one so that will be easier to understand, because here we have too many uh, uh, too many elements. So kx1 to xn is like you have something of the kind a polynomial in x1 comma x2, and yeah, that is a better one, such that f and g belongs to okay, f and g belongs to q. How shall I say, qx comma y. Okay, something like that. So yeah, so you can say that, and gx1 to x1 comma x2 is non-zero. So what I mean to say, you have some polynomial. So okay, so what is this ring kx1 comma x2? What is this ring? This ring means you have all the polynomials, like with the variables, to not variables with, for example, you think of it as a variable, so you have something like x1 square plus a x1 into x2, something like that. You have a big expression, so it's like polynomials in x1 x2. Okay, so this is a square bracket, and if you allow this small bracket, that means you are allowing inverses of these polynomials itself, not polynomial, these are elements, because I have substituted x1 x2 to be like the elements. So you understand what is this field? So for example, here a typical element will be some relation between these xi's, not just linear, any power relation, any multiples, anything is fine, and even divisors. Okay, so let me explain in this situation. So you have g belongs to, I'm saying I need to find this information. So what I can do, I know G belongs to K chi x, right? So that means, and G is what? G is some polynomial where this implies gx is something a0 plus a1x up to and so on an x raised to power. So if you don't want to be confused with this n, you can just take m. You have x raised to power m. You have some this, and am is non-zero because you already know we are talking about non-zero polynomials. So this is well defined. So am is non-zero, and you have gx to be this. Okay. Now where AIs belongs to K chi, because G belongs to this where the coefficients are from K chi. So now what you can do, you just take these AIs, and because what you want this polynomial to look like in a different one, such that you different field where you allow coefficients, like coefficient should belong to this field. So what you can take, you can just take these AIs, because we just need this to be included in the field, AIs to be included in the field, so that this polynomial will be in the field. So you take this this field, because I have taken a small bracket, that means this is a field. You take this, and these are finite numbers. So again, this is a finite number, we don't need to care about anything else. So this is just a subfield or containing K and these AIs. So this, now gx belongs to this. So is this expression clear? So gx is
Yes,
a
yes.
exactly. So gx is a polynomial where coefficients belongs to this field, and that is true because I have just included AIs in the set. So that is our choice which we need, because we just need to prove that if it is algebraic over K chi, then there exists some n and xi such that it is algebraic over this field kx1 to xn. So we just take x1 to xn to be a1 to am in our notation, and m belongs to where m belongs to n star, of course. Okay, because now we know that this polynomial belongs to this field and this is non-zero. So kernel of yeah, kernel of y, because this is a 0 of y, kernel of y comma k a0 a1 up to and so on am, this is non-zero because g belongs here. So y is algebraic over k a0 up to an a. Is that okay now? Okay, so we assume that G is algebraic over K chi, and we prove that there exists some elements, some finite number such that this happens, such that kx, so you have this field, new field, such that G is algebraic over this new field. Okay, any questions on this? Any questions?
No.
Okay, great. So let's do this question. Let L over K be a field extension. If L over K is a prime number, then show that there is no intermediate field E with K subset of E subset of L. So you have three fields, K, E and L. So these are fields we are talking about. Okay, what is this representation? This represents dimension of L over K. Even you can say degree of field L over K. So degree of the field extension L over K. So these are the notations. So okay, so you need to find the dimension of L over K. Not find, it is given that this is a prime number. So prime number, at least this is finite, we know. So let's say this is this prime number. So this means this is finite. Then show that there is no intermediate field. So we are saying you cannot have, so this is the representation, if so to say. So this is a field extension which has degree prime number. Then we are saying either L has to be equal to this or this. Okay, that means we are saying, so basically it's kind of, we cannot factorize P because we have this dimension representation. Yeah. Yes.
Say, on type of result is available. L is to K. Dimension of L is to K is equal to dimension of E. Dimension of E is to L into dimension of
E raised to L. Oh, sorry. Yeah. Dimension of L over E. Yes.
L into dimension of K, E over K.
Right. Exactly. Yeah. Even we can prove that as a vector space. You take a basis. You take a basis of K over E. So you have this. You take a basis. Let's say x1 to xn. Some basis. And you, because this is a vector space, so and you have this basis y1 to yn over this. So over this, okay. So that means yi belongs to L, and we allow coefficients from E in this case, and in x1 to xn case, we these belongs to E, and we allow k linear combination of these xi's. So if you have these two bases, then you know that L over K, the basis for L over K, you can pick it to be x1 by 1, x1 by 2. So basically, in a shorthand, I can write xi, yi, yj, where I and j. Oh, I wrote same notation, so I should write, this could be different. So this is xi, yj, where I is from 1 to n, and j is from 1 to m. Yeah. So this, you can prove that this is a basis. Even like there is no two elements which are same, you will get a contradiction. So because of this, you have so what is the cardinality? This means dimension is dimension of L over K. If dimension of L over K is m into n, because all these, how many of these we have? Xi into yj. You have mn monomials, so to say, or mn elements in the basis. So because of this explanation, we have this equality. Dimension of L over K is same as dimension of L over E. You take and dimension of E over K. So you take L over E over K. Yes. Of this is multiplied to get L over K. So from this, what do you have? L over K in this notation. This is equal to L over E into E over K. Right? So what does that mean? From the first part, it is given that this is one more thing. This is only allowed when you have a finite. So L over K, if this is a finite dimensional. If this is a finite extension, only then you can say, you can use this expression. Okay, finite dimensional. So I should write, this is true if L, or okay, this is in this representation, dimension of L over K is less than infinity. That means this is finite. Then dimension of, so this is the expression I am talking about. Okay, so we have already given L over K is of dimension P, which is a prime number. So this is finite, at least we know. So we can use this definition, use this formula, and so this is given to be a prime number, and so you have this, yeah. So as a numbers, this P, this is a prime number, so it can split either. What are all the divisors of P you have? 1 or P, right?
Yes,
So
yes.
yeah, so what could happen? Either this situation can occur, either this situation can occur. First one is for LE, and this is for EK. So either, so as I said, either L or E could be equal. So what does that mean to say that E over K is equal to 1? That means these are same, the dimension is same, right? So similarly for L over K, so anything can happen. So one of the situation can occur. So either L is equal to E or E is equal to K. So exactly, which says there is no intermediate field, because if it has to be, it has to be equal to one of them. Like intermediate means not equal in both the cases. Is that okay, this part?
Okay, okay.
Okay, so let's complete the second one. If L over K is finite, then show that degree of mu xk divides L over K. Okay, so you have been asked. So I'll just write what it says. If, so as I said, L over K has to be finite to use this formula at least. So to show, if L over K is finite, then degree of mu xk, where x is what? X is okay, so x is some element of L, divides L over K. This is a dimension, so it makes sense to divide, and where and x belongs to L. Okay, so these two things we have. Then degree of mu xk divides L over K. Okay, so how shall we proceed? So mu xk, again, that is a minimal polynomial. We have this notation. We have kx, which maps to, so here we have this big field L. So L is a K algebra. This is this, and any polynomial fx will map to f of small x. So small x is the element we are talking about, and mu, so from this we have the definition. Yeah, so k of small x, that is isomorphic to k of x by mu xk, right? We have this as again K algebra isomorphism, field isomorphism, and vector space isomorphism, that is this is K linear isomorphism. Okay, so we have this much information from this. So okay, how shall we proceed? Okay, so what is degree? Degree of mu xk means, from this information, as we already used this statement also, so from this, what is the degree? Degree of mu xk in terms of dimension of something, dimension of some vector space. What should I write?
Dimension of L over K.
Okay. So L is the big field. When we take the isomorphism, we take this. So even I can. So yeah. Okay. One more thing. L over K is finite. Even from this, we can say X is algebraic. That is also one exercise you can try. If L over K is finite, so okay, let me write exercise. L over K is finite implies X belongs to L is algebraic over K. So what does this say? If you have finite extension, then every element is algebraic. You can try to prove that. So why I stated that, because I can now write K small bracket X, and that makes sense now, because X is algebraic, then square bracket and uh, small bracket, these are same. Basically K, that means Kx is a field. Just you can say that Kx is a field if X is algebraic. So right, you were saying L, but we cannot go to L because the image is itself is just Kx. So from this we know that, from this information we know that dimension of Kx over mu xk is same as, because these are isomorphic as vector spaces, so dimension has to be the same. K algebra means it is isomorphic as fields and it is isomorphic as vector spaces. So you have this statement, and you know that what is the dimension of Kx mod this? It is the degree of mu xk. We understand this well, because we, as I explained earlier, we just take the remainders here, and that will have only whatever degree you have. For example, you have x raised to power n something something. So the dimension will be just, you are allowed to have something like 1 x square up to and so on, x raised to power n minus 1. These are the linear combination of these monomials, so you are allowed to use that only. So these are kind of remainders from this quotient. Yeah, so this is because this is a field, kx is so k is a field, so kx is has this property of division algorithm, and so from this remainder thing you can write this. Anyway, so this is equal to degree of mu xk, so this is equal to dimension of kx. So as I said, so now degree is equal to dimension of kx. Now, so what you are asking, dimension of kx, so question is dimension of kx divides dimension of again this is the dimension over k, because you are saying this is k vector space isomorphism, so the field is k, so dimension of kx over k divides dimension of L over k. Is this true, or even or how can we prove them? Yeah, how
Means network issues have I have not heard.
yeah, so yeah, you can use this first statement thing, you can use this tower. So these three, all three are fields, right? So and you know that L over k is finite. This implies, what do you have? L over k is equal to, so this from this tower you have L over k is equal to L over kx.
L or
Square bracket.
k
Yeah.
into
Into
kx over k.
yeah, exactly. So these are dimensions representation, and this you are saying dimension of kl, and this is your dimension kx over k. So that means what? You have this multiple thing. This implies both of these are the factors of L over k. So that has to divide. So kx divides dimension of L over k. Is that
Yes.
clear? That which you
Yes.
have
Yes.
required to prove. Okay. Any doubts?
Mm,
Okay. So yeah, I'll stop here.